How you doing? I'm Mr. Rose, and today we're going to talk about another conceptual question from Young and Freeman's 13th edition. This is out of chapter 24. It's question 24.5. Again, I have it on the screen here. You should read it, maybe pause, write some things down. Again, I've printed my own copy, highlighted out the questions that I want to ask, so I'll be referring to this as we go on. And as always, just make sure you give a pause and try and solve this problem and think about this before I go out and thoroughly do it. Now, in question 24, it does also give you this diagram, which I'll be referring back to about our parallel plate. So you can see here that this is just like our three-dimensional, what those parallel plates actually look like. Now, this is a cross-section or side view where, as described by the problem, we're going to separate out this parallel plate so the distance is not much smaller than my plate itself. In other words, I can no longer assume for this question that these sheets are infinite. So let's go, and I drew a little bit. Obviously, my picture is not as good as the one from the text, but let's try and go and discuss what we're doing here. The first question is asking is, part A, is it still accurate to say the electric field between the plates is uniform as we separate this out? Well, you should be able to see here that I have this little bow, and again, you can refer back to that picture that we just saw from the text. This little bow, these are called fringe effects. So just by inspection of the picture, I could say, no, I definitely can't assume that I have a constant electric field. I can, but if I look at part of it, the interior, I see that my electric field is constant, and that's okay. We want to be able to see that. But if I'm looking at the entire thing, I can no longer assume my electric field between these two plates from 0 to wherever it ends is a constant electric field. In other words, the larger the distance, you need to take into account that fringe effect at the end of those parallel plates. So it is no longer accurate to say electric field is uniform. Now for part B of this question, they give you an equation. Part B, the equation that they're giving you is the potential difference from A to B, that's just between those two parallel plates, equals Q times distance divided by epsilon 0 times A, epsilon 0 times A. And what the question wants to know is, if my plates are pulled apart as described, will the potential difference be more or less in the formula would indicate? Well, this is actually a little bit easier than part A once we kind of explain part A, right? If I'm looking at V equals Q times D, Q is charge, D is my separation distance, epsilon 0 over A, and I do have some constants here, right? What are my constants? The area of my plate's not going to change. Epsilon 0, that is just the permittivity of free space. That's not going to change. That's a constant. And in this case, I'm assuming right now that Q is the charge, and that's also not going to change. So if I separate out my distance, my electric potential of V should be directly proportional. If D increases, V increases, or my electric potential increases. So last is part C. Now part C is a little bit tricky here. It says, with the plates pulled apart as described, is the capacitance more than, less than, or the same as given by equation 24.2. I've written down equation 24.2. They give us C is equal to Q divided by the potential, which is equal to epsilon 0 times A divided by D. So at first glance, I'm going to say, this is kind of a cakewalk, right? At first glance, from my formula here, I'm going to see that C and D are inversely proportional. Well, if C and D are inversely proportional, as D increases, what's going to happen to the capacitance? The capacitance is going to decrease. But that's not actually accurate in real physics. Again, let's start talking about this fringe effect. And I'm going to interject here just so we might be able to see it a little bit better. This is my capacitance is equal to Q over my potential difference, which is E times D. Now, maybe you see where I'm going with this, right? If I have to account for this fringe effect, What is that actually telling me? That's telling me that the capacitance is going to be larger. Why is the capacitance going to be larger than I expect? Because my electric field is actually getting smaller, right? My uniform electric field, I'm looking at a smaller section of this, so I have the uniform electric field. And if I'm increasing and I have that fringe effect, my electric field is going to be smaller than if I have a small distance and these alleged infinite sheets. So, if I'm deriving my C is equal to Q over E times D, and I assume my electric field is uniform because that's where that came from, my capacitance has to get bigger. If distance decreases, if distance is increasing, my electric field has to decrease. So I really want you to think about that. Again, essentially, my capacitance has to be larger because my expected electric field has to be smaller. And it's made very clear because epsilon 0 A over D is going to show me, sorry, I lost my train of thought. It's going to show me that the electric field, or my uniform electric field, had to be made smaller. That's all I have for you about this problem. By all means, please feel free to like, click, or subscribe, and you'll see me next time. Hey there, folks. I know you said you'd see me next time, but I just cardinal sin rewatched the video, and there's a key word that I didn't put in. When I just kept saying the electric field is going to be smaller, the electric field is going to be smaller, the word that I'm uncomfortable with and now I want to add into it is the magnitude. Well, the magnitude of the electric field on average is going to be smaller because my uniform electric field is going to be in a much more condensed spot. That now is all I actually have for you. Again, please feel free to like, click, comment, or subscribe. I've been told clicking is nothing, so I actually don't know what I mean by that. But thanks again, and you'll see me next time for real.